Yeah, very good morning. Welcome to Electromagnetic Waves and Transmission Lines course. And today's topic is Smith chart. And this is Dr. Pandu Rangaiah, Associate Professor, Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering. In this class, we will cover about the formation of the Smith chart, which consists of the two kinds of the circles, which are the R circles and X circles. So how that those R circles are formatted, and also the X circles are formatted, and how that the Smith chart, which consists of both the R and X circles, and how the Smith chart is obtained. And after completion of this class, the students will be able to understand the concept of the formation of both R and X circles, and also they will know that and how to construct the Smith chart from the basics of those the reflection coefficient. So to go with these the Smith chart, or to know that the formation of the R and X circles, we'll start with the reflection coefficient, where we know that the reflection coefficient expression, which is the K equal to ZR minus Z0 by ZR plus Z0, where ZR is the terminating impedance and Z0 is the characteristic impedance. So we'll start from there the reflection coefficient, and which is a complex constant, and which is a vector quantity which has both the magnitude and the direction. So now here in the reflection coefficient, I will divide both numerator and denominator with Z0. Then it will becomes the K equal to ZR by Z0 minus 1 divided by ZR by Z0 plus 1. I will assume here the ZR by Z0 as the normalized terminating impedance. So I am taking the load impedance, the terminating impedance, with reference to the Z0. Therefore, I am assuming ZR by Z0 as the normalized terminating impedance, Z suffix small r. Then the reflection coefficient K, we can write it as an K equal to ZR minus 1 divided by ZR plus 1. Or by solving this expression, then I will also write the ZR as 1 plus K divided by 1 minus K, where the Z suffix small r is the normalized terminating impedance and K is the reflection coefficient. Both are the complex constants. Both are the complex constants. Therefore, I am writing ZR the normalized terminating impedance, which has both real and imaginary parts. I am assuming it is an R plus J capital X, where R is the real part of the normalized terminating impedance, X is the reactive part of the normalized terminating impedance. In similar way, the reflection coefficient also it is a complex constant which has both the real and imaginary parts. That also we are assuming it is an KR plus JKX, where KR is the real part of the reflection coefficient and KX is the imaginary part of the reflection coefficient. Therefore, if I substitute this normalized terminating impedance as R plus JX and the reflection coefficient as the KR plus JKX in this the above equation, then the R plus JX is equal to, we can write 1 plus, in the place of the K I am writing it as an KR plus JKX divided by 1 minus KR plus JKX. So to get again this on the right hand side equation expression in terms of the real and as well as the imaginary parts, I am rationalizing this equation. Means I am multiplying with this equation, I am multiplying both numerator and denominator by using the term 1 minus KR plus JKX divided by, and again I am multiplying with 1 minus KR plus JKX. So rationalizing this equation with this the term, then we'll get it is an, this is the expression. And again simplifying this, we'll get R plus JX is equal to 1 minus KR square minus KX square plus 2JKX divided by 1 minus KR square minus JKX square. So I am equating both the real and imaginary parts of the above equations. Then I can write R equal to 1 minus kr square minus kx square divided by 1 minus kr square plus kx square, and I am calling that as an equation 1. And the imaginary parts are also by equating on both the sides. Then we can write the x is equal to 2kx divided by 1 minus kr square minus jkx whole square, or which is equal to kx square. So these I am calling this an equation number 2. These equation 1 and equation 2 are represents the family of R circles, the equation 1, and whereas equation 2 represents the results the family of X circles. I'll repeat once again. So to construct it is a Smith chart, we considered the expression for the reflection coefficient, which is k equal to ZR minus Z0 divided by ZR plus Z0, dividing both numerator and denominator with Z0. Then we are assuming ZR by Z0 as the normalized terminating impedance. We got k equal to ZR minus 1 by ZR plus 1. And from that the equation ZR equal to 1 plus k divided by 1 minus k, where the ZR and k are the complex constants. Therefore, we are assuming the ZR as R plus Jx and k as kr plus jkx, substituting and rationalizing those equations on the right hand side and equating both real and imaginary terms on both the sides. And we got the two equations where r equal to something and x is equal to something, and we are calling it is the equation 1. The real parts by equating on both the sides, which is the family of R circles. The imaginary parts by equating on both the sides, whichever the equation we got, and we call it is the family of X circles. But whereas the circle expression is nothing but it must be looks like x minus a whole square plus y minus b whole square equal to something like it is an r square. So this is called as a circle, general circle equation, where for this circle the center is, we can say that a comma b is the center and the radius is the r meters, like that. So we want to make that these equations are also to put in the standard form of like kr minus something whole square plus kx minus something whole square equal to some constant square. Therefore, we'll consider the equation 1 separately and equation 2 separately, and we'll put in the form of those circle equations. Let us consider it is the constant R circles. So let us consider that the equation 1, and we'll simplify this equation 1 and put in the general form of circle equation. So considering this R equal to this equation, cross multiplying on both the sides, and we got this is the expression where if you look it is this expression here, this is of having like kr square minus 2 into r divided by 1 plus r into kr. So it is kind of like this, kr square minus 2 into r divided by 1 plus r into kr. And the other term which is missing to write it is a perfect square is, suppose if I add r divided by 1 plus r square to this term, if it is available, then this expression I can write as an kr minus r divided by 1 plus r whole square. Therefore, this r divided by 1 plus r square term is missing here to write it as a perfect square. So I want to add that term on both the sides of this equation, right? And whereas if I consider the kx square, only kx square is there with respect to the kx term is concerned. Therefore, directly I can write this as kx minus 0 square. That is also perfect square I can write. So for that, kx we can write like this way, whereas the kr terms to write it is in a perfect square, we need to add r divided by 1 plus r whole square on both sides of this equation. So by adding that term on both sides of that equation, so then I can write by I am adding this onto the left hand side and as well as the right hand side. Therefore, the value does not changes. So if I adding like that, these are first three terms together. I can write it is a perfect square like kr minus r divided by 1 plus r whole square plus kx square is the other one, equal to By simplifying this, 1 by 1 minus r divided by 1 plus r, I am adding r square divided by 1 plus r whole square, the term. And by simplifying this expression, the LCM I will get, it is n for these are two terms, 1 plus r square. This is an 1 plus r, this is a 1 plus r square. Therefore, 1 minus r into 1 plus r means a plus b into a minus b, a square minus b square, plus it is an r square. Therefore, this will be becomes 1 divided by 1 plus r square, or I can write 1 divided by 1 plus r whole square. So now if you look at this equation, this will be looks like is a circle equation where it is of having kr minus r divided by 1 plus r whole square plus kx square equal to 1 divided by 1 plus r whole square. It should be looks like x minus a square plus y minus b square equal to some r square. So where it is of in the place of a, it is of having r divided by 1 by 1 plus r, and in the place of the b, it is of having 0. In the place of this r, 1 divided by 1 plus r. Therefore, this equation represents the family of circles or circles onto a reflection coefficient plane, which consists of its radius is 1 divided by 1 plus r, and having the center is at r divided by 1 plus r comma 0. So the first equation, if I add, it is an r divided by 1 plus r whole square on both sides of that equation, and simplifying that, it looks like it is a standard circle equation form, which consists of its center is at r divided by 1 plus r comma 0, and having the radius of 1 divided by 1 plus r. Now it is, if I change the r value, if I take it is an r is nothing but the real part of the normalized terminating impedance, which varies from 0 to infinity, positive values it takes. So 0 to infinity, if I vary that the r value by taking 0, 1, 2, so on infinity, it gives the different circles. Therefore, as the value of r is changed, that equation will be gives is an different circles, which we can call it is an the family of r circles. So that we will see that I will take it is an these are circles, a constant reflection coefficient plane. I will take it is an the kr axis, and this is an the kx axis. This is the kr axis I will take, and this is the kx axis I will take, and these r circles of having the radius is 1 divided by 1 plus r, and the center is r divided by 1 plus r comma 0. Let us I will take it is, and the first circle is assuming r equal to 0. If I take the r equal to 0, the radius is, if I substitute r equal to 0, the radius will become as an 1 divided by 1 plus 0. It is, and the radius is the 1. And again the center is r equal to 0 is nothing but 0 comma 0. 0 comma 0 divided by something is 0. 0 comma 0. Therefore, the center is at 0 comma 0. This is center if I assume 0 comma 0. And the radius is an 1 meters. Assume that this is an 1 meters. 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 From this center. If I combine all these together, so this is the circle where the center is at 0 comma 0 and the radius is at 1. So this point will be becomes as an, this is an 1 comma 0. The radius is 1 meters. This is an 0 comma 1. This is also like this. So this is an R circle which is R equal to 0. R equal to 0. Suppose if I take it as an R equal to 1. R equal to 1. If r equal to 1, the radius is 1 divided by 1 plus 1, 1 by 2, means the radius is 0.5 meters and the center is at r equal to 1, 1 divided by 1 plus 1. So it is also 1 by 2, means it is an 0.5 comma 0 is the center. 0.5 comma 0, assume this is the center. This is the center. From here it is the 0.5, from here to here it is a 0.5. From here to here it is a 0.5, from here to here it is an 0.5, assume that this is the point, this is the point. So therefore, we will get a circle like this. This is R equal to 1 circle. If I have been taken R equal to 0.5, may I got it is an, this is a circle. This is an R equal to 0.5, 0.1, assume that. If it is an R equal to 0.5, may I got like this. This is an R equal to 1. This is an R equal to 2. R equal to 5. R equal to 10. R equal to 20. R equal to 50. R equal to 100. Suppose if I take R equal to infinity. If R equal to infinity, 1 divided by infinity, which is and the radius is equal to 0. And this is, the center is at R equal to infinity, nothing but that equation I can write 1 divided by 1 by R plus 1 comma 0. R equal to infinity, something divided by infinity is 0, means it is at 1 comma 0. 1 comma 0 is nothing but this point itself. So, R equal to infinity is the point itself. So, these are all circles are called as the constant R circles. So, the previous equation, which is represents that the family of R circles of having the radius is 1 divided by 1 plus R and the center is at R divided by 1 plus R comma 0. If I take the values of the R as the real values from 0 to infinity, I will get the different circles, and all these circles together are called as the family of R circles. The family of R circles neatly have been represented here. See that this is R equal to 0 circle. This is an R equal to 0.2, R equal to 0.5. Then this is an R equal to 1, R equal to 2, 5 and 50 and so on. It is an R equal to infinity circle is a point itself, which is the same point itself. And here, if you notice that all these circles, the constant R circles, are touching a point called is an 1 comma 0. All the circles are touching, including that the R equal to infinity circle also touching the point 1 comma 0. Right? Similar way, I will go ahead with the constant X circles. I will take the equation number 2, where the imaginary parts on both the sides of that equation, the reflection coefficient equation, by equating the X is equal to, we got this equation. I will also again start to simplify this equation. I will put in the form of the standard, the circle equation. So together the standard circle equation, if I rewrite this and we got this expression. We got this expression. In this expression, suppose the KR terms, if I see that, so KR terms is, all these KR terms, KR square is there here, minus 2 KR is there, and plus 1 is there. This directly I can write it is an KR minus 1 whole square I can write. KR minus 1 whole square I write. The remaining terms of the KX if I take, we have it is an KX square and minus 2 KX divided by X is there. So if I want to write this also as a perfect square, another term which is missing is some X is there here which is missing. Like it is an X square minus 2AB. So here A square minus 2AB. B square is missing here. So if I add it is an plus 1 divided by X whole square here, then also you can write it is an, this also it is like KX minus 1 by X whole square we can write perfect square. So for that, what we are doing it is, for this equation, I am adding 1 by X square on both the sides of above equation. If I add 1 by X square on both sides of above equation, we may get, the first one it is the KR minus 1 square I will get. The other one it is KX square plus 1 by X whole square minus 2 KX divided by capital X. This I can write a perfect square of KX minus 1 by X whole square, which is equal to 1 by X whole square. So this is also looks like it is a circle equation of X minus A square plus Y minus B square equal to R square. Therefore, whose center is at 1 comma 1 by X and the radius is 1 divided by X. So here these all the circles are in terms of the imaginary value which is called as the reactance which is called as an X. whose center is at 1 comma 1 by x and the radius is at 1 by x, where x is the reactance of the normalized terminating impedance, which it takes both positive and negative values. The reactance will take it is an both positive and negative values, so that we have it is an the variation of the x from minus infinity to plus infinity. It may be of having positive values and as well as negative values. So now I will take this x value. I can vary from, I will take it as an both positive and as well as the negative values. To draw that those the x circles, I will take it is an the kr. This is the kr axis and this is the kx axis. So where it is in the center, if I consider above to this horizontal axis, I will take it is on the x is of having positive values. Below this one, it is of having the x is equal to negative values. So above x, the positive values is nothing but which is called as an inductive circles, and below that the x which is of having the negative is called as an capacitive circles. Now I will take it as an x is equal to 0. If I take x is equal to 0, then the radius is infinity and the center is at 1 comma infinity. So 1 comma infinity, this is the 1 comma infinity. It looks like it is in a straight line. X is equal to 0 is a straight line, which is an horizontal line, which is of having its radius is infinity, and it is of having its center is at 1 comma infinity. So it is like it is an kind of it is in a straight line. If I consider it as an for easy understanding purpose, if I take it as an x is equal to 1, then the radius is 1 and the center is at 1 comma 1. The center is at 1 comma 1. 1 comma 1 is nothing but this is an 1. 1 comma 1 somewhere else here. This is 1 comma 1. This is 1 comma 0. Okay. And this is the point is 0 comma 1. Okay. And this circle is of having the x is equal to radius is equal to 1. So from here to here the radius is the 1 and from here to here the radius is the 1. If I draw that circle is like this. This circle is x is equal to 1. Suppose if I take it as an x is equal to 0.1, this circle may be like this, it comes like this, right? And x is equal to 0.5, it may be like this, okay? And if we take it as an x is equal to 2, it may be it goes and again it comes back, x is equal to 10, x is equal to 20, like this, the circles. Similarly, if I take x is equal to minus 1, right, or x is equal to minus 0.1, the circles will get like this, like this, like this, like this, like this. If I take the x is equal to infinity, if x is equal to infinity, the radius is 0 and the center is at 1 comma 0. 1 comma 0 is nothing but this one, the radius is 0 is nothing but the point itself. So here also all the x circles are also touches the point 1 comma 0. If I neatly to see you here. So I am taking it as an only a portion, half portion of the x circles. I am not drawing here. R is equal to 0 circle is taken. This is an the outermost circle. And if I draw that all these x circles, this is an x is equal to 0, which is an straight line itself. And this is an x is equal to 0.2. And this is an x is equal to 0.5. X is equal to 1. X is equal to 2, x is equal to 5, x is equal to infinity. Similarly, x is equal to minus 0.2, x is equal to minus 0.5, minus 1 and all these things. So these are all by varying the x value from minus infinity to the plus infinity, we got it is an the circles, different circles. So therefore all circles together we will call it is an the family of constant x circles. The family of x circles. So if I draw that both X circles and R circles together onto the same circle, then it is called as the superposition of, or we can say that superposition of both R and X circles together is called as an Smith chart. Therefore, the Smith chart is obtained by the superposition of the two sets of the circles, which are X circles and R circles. Therefore, all X circles are also passes through the point 1, 0, and all the X circles are also touches the point 1, 0, and this is called as the center of the Smith chart, right? And these are all called as an R circles. The outermost circle is called as an R is equal to 0 circle, and this straight line is called as an X is equal to 0 circle, whereas R is equal to infinity and as well as X is equal to infinity are the circles which are the point itself vary at 1, 0. Therefore, R equal to infinity and X is equal to infinity circles are there on the right hand side of this Smith chart, whereas R equal to 0 and X is equal to 0 circles are there on the left hand side of Smith chart. Therefore, the Smith chart is a graphical representation of the superposition of both R circles and as well as the X circles. And this is the complete the Smith chart, which it consists of both R and X circles together, and where this the point is called as the center of the Smith chart, which is called as the center of the Smith chart, right? So these are the textbooks which to be followed to go through the topic. So before to summarize, we learned in the class how that the Smith chart is obtained from the reflection coefficient equation. So we consider the reflection coefficient equation and we took it as the normalized terminating impedances, whereas the reflection coefficient and the normalized terminating impedance both are the complex constants. We wrote in terms of the real and imaginary parts, and we equated both real and imaginary parts of those equations. We got it is in two equations, and those two equations we put it is in a standardized circle form, and where we varied R values and the X values so that we got it is in a different family of constant R circles and as well as the family of X circles, and the combination of or superposition of both R and X circles together is called as an Smith chart. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.